Oh, we weren't assigned a breakout room. Yikes.
Yeah, I noticed.
Yeah, I was having some technical issues. Do you want to just like make a board on the far right? Oh wait, okay, I just got an invite.
Yeah, me too. All right.
Okay.
And then, what's the name of what we're returning?
The longest
Is it just
increasing substring
longest
subsequence.
increasing substring? All right, let's call it longest increasing sub. Is that empty?
Hello?
Hello.
Oh,
Hello.
okay. I wasn't assigned a breakout room.
Oh, okay.
Oh wow. Oops.
Welcome.
All right, so far for this algorithm, I'm thinking we start at each index and we try to find one that's one bigger in the list. If we can't do that, we do two bigger and we keep incrementing until we find one. And then we repeat that for each number until we get to the end. Oh, whoops, I'm not writing on ours.
Oh.
Let's see. Here we go. Okay, that's better. What do you guys think about what I have there? Try to make sure this makes sense. So I'm saying if you do find a number that's one higher, then you go to the next index in the list. But if you can't, then you increase what you're finding higher by. So it would be 2 next time.
Yeah. It's just that on the Miro board, I don't think it's going to update what you're typing until you finish
Oh,
in
shoot.
that text
Okay.
box.
Is
There
that
we
showing
go.
up now? Okay. My bad.
Oh. Yeah, that looks good.
Okay.
Yeah, that makes sense.
And then at the start of each loop, we set this. And then at the end of the function, then that last step I just put in says if you run through that recursion, you find a substring longer than the longest one you already have, then you redefine your longest.
Looks good.
Alrighty. Guess we can try to plug in that list and see what happens.
Oops.
All right, and how is this group doing?
Pretty good.
We're chugging along.
Chugging along.
Yeah, I'm still gonna verify my algorithm to make sure it's actually working, but I put down every idea that I had.
To find your board.
I think I'm on the right track, but I'm not 100% sure it's actually gonna work yet.
Seems solid to me, but I'm just trying to think.
Basically,
of
what
how
I
that
was
would-
thinking is you look for a number in the list that's one higher, and if you can't, then you increment it and you do two higher, and you keep doing that. And then you also increase your index, and you do that for each number in the list, and you increment that as well.
How much higher? Okay, so you're defining a subroutine here, which is find next in list, which gives you how much to increment by, and the index is where you currently are. Is that what you're saying?
Yep.
And the index, we assume that the string at index is, we want to include it. Is that right?
What do you mean include it?
Yeah.
So is index in our list or not?
Yes.
Okay. So if num found, and what is num found?
Num found is if you find a number that's how much higher in the list.
Okay, so if anything, so maybe formally write down how do you get num found. So I think
Okay.
maybe you need to define what that is.
So just another function in there we could add.
I think you can just declare what the variable means,
Okay.
like right above that if statement, maybe. Now, does your algorithm account for, so let me see how the solution I give, so we have one. Oh, these are all different by one. Oh, no. So from 3 to 4, we're adding 1. From 4 to 5, we're adding 1. And then from 5 to 6, we add 2. So this is kind of, it seems like it would work. But then from 6 to 7, we add 1 again. So is there a way to decrement your how much higher?
Oh, I was thinking for every index you start at 1 for how much higher. So I'm gonna have to take that into account as well.
Okay.
Because every new number you start on, you want to see, hey, is there one higher?
Right. And then if there's one higher, we return that one.
Or you keep going throughout the list, is what I was thinking.
Okay, so then I don't see the algorithm to solve the whole problem then. So this is a subroutine, right?
Currently, yes.
Yeah. All right, yeah. So for each index, you're gonna call how much higher how many times? Or
Until
find
you
next
get
in-
to the end of the list.
What does it mean to get to the end of the list? Because I'm not changing my index, right?
Yeah.
So if
So-
I fix the index, how many times do I call find next in list?
Find next in list. My goal was to call it until you reach the end of the list. So say you start at one higher and you can't find anything, then you go to two higher. And you would keep doing that until you found a number that was higher. And then you would change your index.
Okay.
So
All
I
right.
want to.
How about you write the whole algorithm down?
Okay. Yeah, I'm defining
Yeah.
num found right now.
Others should feel free to speak up too. I'm a little suspicious of this approach. You should be too, trying to figure out what are the invariants that he's preserving here.
Yeah.
So there
We
is
need
a
to-
way to use this that would work. Well, no matter what, the recursive thing is not going to be optimal, but there's going to be a kind of faster thing you can do rather than incrementing how much higher by one. But let's stick with this for now to get to the full algorithm using this one.
I think we need a loop under the first find next in list, where you just loop through until you're at the end of the list. Right?
So have our third line under our find next in list.
No, I think add another loop.
Another loop.
Or else yeah. Because then you find the largest substring for that index.
Yeah, let's also separate out the I see I missed the for loop there before. The subroutine, so maybe put that down further and then calls to the subroutine as well. So that way it's a little cleaner.
You mean like for number 2 when we plug in the numbers?
For number 1 here, so I would can maybe hop in there. Just hit enter a couple times so that here's my subroutine under here, right? This is the definition of the routine, right? And then up here is the first algorithm. So that way we separate them out. And so we should call this somewhere up here. I don't know if this is, yeah, possibly what you want to call it, but so separating out the calls to it from the definition of it.
We can't see what you've typed in the box until you get out of it.
Sorry. There we go.
Okay.
I almost want to get rid of the first loop too. We could just deal with everything inside the function. So I'd say we could make this function run for each index, and then we could, afterwards, we could just loop through each index with
Okay.
it.
Maybe update that. Let's try it.
Okay, I'll rework a few things.
Okay, I'm gonna hop into another group to see how they're doing.
All right, thanks for your help.
Um,
Oh, looks like we're out of time.
Are we being called back already?
On my end, it is.
Oh yeah, shoot.
Well, I guess that's all we got.
Okay.
Close enough.
I'm curious to see what the solution.
Oh. All right. Okay, so one thing that I think most of the groups, a lot of the groups have noticed is that we need what I call helper functions that solve a similar, I'll say a very similar problem. Maybe with one added constraint or small or few added constraints. Okay. Now, there are two kind of sub-problems that are, I guess, similar problems that could have been solved. And actually, maybe I'll let you kind of tell us what are the problems that you have found here.
We have to be able to identify whether we're looking at an increasing subsequence or increasing sequence, I guess.
Okay, so that's, yeah. Yeah, also might need additional functions. Such as, we'll say, is increasing. Right. Whoops, which would take so we could need to define other things, right? Because if I could put a loop in there to check to see if this is increasing, but then I would have to, go through this loop, and that loop is adding some mess to my code. And the best type of code is the one, or even algorithms, the one that is super easy to read, right? So from you name your functions well, you kind of in their names, so that way it's almost like reading English as you go through this, right? And so if you take that loop, which loops are kind of detracted, figure out what's going on, right? If we extract that into a function itself, then we can just we can say, okay, this is what this function is. Takes as input an array, returns true if the array is increasing, it's false otherwise. Yeah, were there other functions that we would want? So here's one of them, I guess. Right, and we might not use them all too, so there's different variants of things. Maybe I should say here that the signature of our function should be, in the end, I'll say, we'll call it longest increasing subsequence, and takes as input one array. Okay. Anything else we would need to put off into a different type of function? Did anyone else have another subfunction or similar recursive type problem?
we had the helper function build, excuse me, build sequence, but we're not really doing it recursively, but more just iteratively.
Yeah, okay. I'll put that, here we go. All right, and what was the function called?
We called it build sequence, and it was basically building out the sequence for any given element, looking at the elements that come after it in that subarray.
And what does build sequence take?
It takes in the array at a certain index and but only considers the array from that index to the end.
Okay. So we can just say that it takes an index and then calls to it would just be subarray, or yeah, subarrays, right?
Mm-hmm.
Oh, there's a deer. Not allowed to hunt in my backyard though.
Can you show us?
Oh. Hold on. To decompose everything. Okay, you have to tell me if you can see it. Oh, there's a baby too. Can you see it?
Go up.
There we go.
Aww.
Aren't they so cute?
Marvelous. Thank you.
Yeah. I call them my dear friends.
Aw.
Actually, there's I don't know, the one's not as big as them. There's a mom and a baby, not these two. That one, they're both kind of young here. That come through and they like sleep really close to our house. And then one day there was 4 other deer who came in. And then I heard this ruckus in the backyard. And so I look out and one of the other deer was hissing at the baby, at the little fawn. It was literally just 2 weeks old or so at that point. And so I came out and I yelled at the deer, the 4 big deer that were being bullies. And then they ran away. And then the mom and the baby were just hanging out, laying down under our apple tree. I felt like we understand each other. I couldn't believe that it was hissing at the baby. Anyway, okay. So I'm trying to figure out what your build sequence does, which
So it returns the length of the sequence that can be built by any given element. So if you passed it in your examples above, if you passed it index 0, it would return 5 because it was able to build a sequence of length 5 for the starting element 3.
okay.
If you passed it index 1, the top example, it would return 4.
All right. And then was that were there any other constraints or no?
No, but we were still kind of like thinking things through.
Okay.
It was a work in progress.
Yeah, I'm gonna call this one roughly equal to the yeah, because actually this is what in the book, in the textbook, he just has it return the actual okay, I can do this. I can move it. Come on. There we go. Right, so they kind of take the same thing. Maybe this one returns the subsequence, and this one returns the size. Right, and I would actually consider these kind of equivalent problems because if you have, if you understand the solution to one, you can update it to get the solution to the other one. Yeah. Were there any other functions that people defined or stuff or?
I guess for our group, you were in our little area and talking to us about what we could do, and you helped us define the list bigger function that took in a value and then took in the array and returned the longest increasing substring of that as an upper value. We just weren't too sure what to do with it after.
Yeah. Okay. So let's go into this. Oops. Okay. For example, LIS bigger, which is what Jeff defines in his book, which, so there's a little bit of optimization in here in that we're not passing the arrays. We assume that the array is a global variable now. And A is a global variable. Or maybe it's, an object, so it's stored in that object or so. And so this returns, and you know what? I'm gonna rename your function and my functions down here. Because build sequence kind of sounds like it wants to return the sequence. And this LIS, it's what Jeff does in the text, is returns the size of longest increasing subsequence. Size of longest increasing subsequence of A, J through N, such that all elements greater than or equal to A sub I. Okay. And okay, so let's go into this. Yeah, that group kind of had a cheat because I kind of pushed them in this direction a little bit too. But let's suppose that we have a partial solution, right? And this is kind of where recursion helps us. Like we think about this as like iterative subproblems. They're all very similar. At some point we need to call again. So let's pretend we've made it through. Partial solution. Okay, and suppose, let's do my example. Okay. Now suppose I have this, right, and I've done part of it. So I want to know, so I've gotten through, say, maybe up to 2. Okay. So at this point, I've built my current best solution already, and I know that 1, 4, 5 are going to be in it. Okay. And so I've taken out, which means I'm not doing 3, 1, 9. And the other question is 2 in the longest increasing subsequence or not? Okay. And actually, I think with this algorithm, we would have 3 instead of 1. So let me just, that way if you step through it, you'll do the right thing. Right. And how could I decide if 2's in it or not? And someone think of a recursive call that we might be able to call. So as we have pieces of it, what's a similar subproblem then? Or we're not even there yet. If I know that this is my partial solution, is 2 in it? Is 2 in my solution?
No,
And how do we know this?
because the last number was 5.
Right. Yeah. So we can add, we have a partial solution already, which is 3, 4, 5. We can add 2 to it. We can call that is increasing subsequence, right? Or we could just compare 2 to that last one. So this is like a clearly no. This is almost like a base case. No. Right. Now the question is, oh, yeah. Okay. What happens if I stopped it at a different point? Okay. So now suppose I stopped it. You know, I'm running my algorithm. I've stopped it here. I know that 3, 4, 5 are in it, but I know that 1 and 1 are not in it. Now the question is, do I include 9 or not? Well, it's valid, right? We know we don't want to include it, but what are the things that I can do? But do I, yeah, but maybe how do I know whether to include it or not?
Could you do 2 recursive calls, 1 including 9 and 1 excluding 9, and then run on the rest of the array?
Yeah, exactly. 2 recursive calls. Okay, so we remember that this chapter is on backtracking, which is basically try every option, right? Try to include it, try not to include it. Yeah, actually, that would bring us to insert my device, and I've grabbed screenshots from the book. Okay. Okay, and so here we are with this is the solution that's kind of coming to. So this is a subroutine though, right? Because I'm solving a similar problem. This I thing is not supposed to be a part of it, but okay. So if j is bigger than I, or is greater than n. Okay, so this is kind of a base case if there's nothing to check, right? So this is my base case. Here, right, this is what's happening, what happened when we check 2. 2, right, is we said 2 is clearly not in it, right? We know that. So let's move on. So then we're going to try this call. We're going to try this again and we move on. And now we ask, is 6 in it, right? So here, right, this is the case that when we check 9 here. Okay, where we check skipping it. So that means that we're going to just keep I as our last one that we need to be bigger than, and then start the array next. Or we can take it, which means that everything in our subarray needs to be bigger than j, right? So this is our, yeah, does this makes, and then we return the bigger of the 2. Does this make sense to you? Does anyone have questions about how this works? Okay. Now, okay, but the one question is, it's not this, the signature I wanted was LISA. So we're going to have to update this, right? So that, right, we want our signature to be LIS taking in an array A. And what we do is we just start with let's see. Maybe I'll do it the way Jeff does it in the textbook. A of 1 through n. And we'll define a of 0 to be minus infinity. Okay. And then we can just call return LIS bigger of, we went index I, 0. And right, so and any integer is going to be bigger than I. And we're going to start at 1, right? Okay. So, yeah, okay. That's what we have here. So this is, and then in Jeff's language, Jeff Erickson's language here, we say that this is a sentinel value. Okay, so this is really the function, right? But the recursion is here, right? So this is just kind of tells us how to call our recursive function. So this is our recursive function. Who can tell me what the runtime of this is? And I know that at least one group has an answer to this. I think all of you do, though. I'm trying out all possibilities of a sequence, right? All subsequences, right? And if I consider this as a set, I'm actually looking at all subsets. So knowing that, what's the runtime?
N squared?
Going to be exponential.
Yeah, it's exponential. Theta of 2 to the n. Yikes. And this is because brute force tries all subsequences. Okay, now I'm going to write this as a recurrence relation though. So not the recurrence relation. Yeah, I'm going to write out what is the recurrence. So the recurrence that we're looking at is, I'll say note, right? And I'll put here mathematically, right? We're going to have LIS bigger. Okay, this is a piecewise defined function. So it's going to be 0 if j is bigger than n. Okay. Right, that second else case, we're going to have LIS bigger of I j plus 1 if a sub I is less than or equal to a, oh no, sorry, it's greater than or equal to, a sub j. Okay, oh, and this last case is gonna, you know, it's a little bit more painful, but it's gonna be the max of two things, of LIS bigger of I j plus 1 or LIS bigger of j plus 1 otherwise. Okay, now I think it was Mike who might have the answer for this one. I think you were the one who just spoke up. the other runtime. But how many, oh, I need to make sure to put I and J in here. How many distinct calls to LIS bigger are there?
I mean, I'm just going to say that there are going to be quite a few.
As we proceed forward, we need to keep that in mind. Because, if they
how many values can I
they'll
take?
throw a stop to the whole process. So,
how many values can I take?
There can be n different values for I
Mm-hmm.
as it iterates through A.
And how many values for J?
N minus I? Or no, just N.
Yeah, we'll just upper bound it. Because if you make sure that it's bigger, it's asymptotically going to be the same. So if I have n values for I, combinatorially, right, how many ways can I have the pair ij?
N squared?
okay.
Yeah, so there's only n squared different values, okay? And which means that I'm calling this multiple times, right? Like, because if there's only n squared values of this, but it's exponential, like there's n squared different functions I can call, right? Exponential runtime. That means that I'm calling LIS bigger of IJ multiple times, right? And diving into that recursion tree, right? Let's say I'm diving to recursion tree. Okay, and the solution for this is to save my results. Okay, and this is called memoization. Okay. And we can do it just one way. Option one is, I'll call it the ad hoc version, right? So I have my table of values of J and my table of values of I. And each time I run into this call, right? And if my first time calling, save the value. If called again, use save value, right? Okay, so it's, we have this table and it tells us whether or not we called it before. And each time, if we've called it before, we just know what it is. If we haven't called before, if we, if we haven't called it before, then we have to go into this recursion, but we only do this recursion once. And the option two, which is smart ordering. Okay, so and this one is, we know which order to call things in. Okay, so for here, so this is my values of J, 1 to N. There's my values of I, 1 to N. In order to call this IJ1, right, which values does it depend on? Right? So IJ depends on, well, we have to be able to compute IJ plus 1. And J plus 1. Okay, so, oh, and there's a question. Oh, there's answers to my question. We'll come back to that in a minute. Oh, it's now 9:17. Sorry. Thank you. All right. Yeah, so we're going to leave it with that, and we'll talk about dynamic programming next time. So I'll see you.
Thank you.